I'm pleased to introduce today's session, Milvus in Action, the vector database behind Troop's shareholder activism, and our guest speaker, Zen Yui. So this is Yui. Yui, do you mind to introducing yourself to everyone here?
Of course. Hi, and Steffi, thanks so much for having me. My name is Zen Yui. I'm the co-founder and CTO at Troop. In short, we are a shareholder activism and proxy advisory company. We use machine learning to do a whole bunch of stuff in this space that we'll talk about soon. So thanks so much for having me.
Of course. So firstly, we just really want to get to know Troop. Could you provide a brief overview of Troop and the service you offer?
Yeah, of course. If you don't mind, I've got some slides about this, so I could just get right into it.
Yep, sounds great.
Sure thing. So thanks everyone for joining. Very pleased to be here. And before I tell you about Troop, I just want to say that Troop and our engineering team owes so much of our success with machine learning and Gen AI to listening to cool talks from other folks who are hacking in this space and with these tools. And so I'm hoping that today, in listening to what we've built and how we've solved some of our problems, that you might be able to cherry pick part of this for your own work and maybe unblock yourself in something that you're hacking at. Also, at the end of this talk, I share my contact info. More than happy to link up with everybody and talk about shareholder activism, Gen AI, or whatever it is you're working on. And so today, this talk is going to be about using large language models as part of structured data pipelines, creating labels out of unstructured data at scale, and unlocking a whole world of machine learning potential for your company. Also, we're going to be talking about using Gen AI to compress data down to something that you can train smaller models with downstream, and maybe even layer in some traditional supervised learning techniques. And of course, how all of this is made possible, storing our embeddings at scale with Milvus. And before I get into how we do all of that, just a quick background about myself. So before Troop, I was a big data engineer, working with kind of batch and streaming systems. I was working with data corpuses around 100 terabytes. And I define big data in two ways. One, it's something that can't be wrangled on one machine or not easily. And two, it's just a size of data that's generally uncomfortable to manage and where processing takes a lot of time and planning. And I find that the most worthwhile data problems don't fit in memory. And yet so many of the hello world examples of doing kind of RAG and a lot of these in-context learning techniques, the hello world examples are very much one node examples. And I understand why, using in-memory databases. And so today, I want to talk about applying a lot of these techniques to larger distributed data, how you do it, how you can use Milvus kind of with a data set that spans multiple machines, and an amount of data that you wouldn't want to process all at once. And so with that, let's quickly talk about Troop. So Troop builds technology that lets everyday investors govern publicly traded companies. And the reason why is that we all own stocks of these companies. We are shareholders. Those shares come with a right to vote. And so it means that corporate governance is our collective responsibility. It's something that not a lot of us think about when we buy stocks on Robinhood, but those stocks come with voting power, and these corporations make important decisions that impact our lives. They even impact policy in our cities, et cetera. And so, Troop, the origin of Troop dates back to the blip in the matrix. I don't know who remembers this, but about 2 years ago, a bunch of Redditors got together on a subreddit called Wall Street Bets and collectivized around GameStop, a stock. And we were super excited about this moment in history because it represented the first true example of multiplayer finance, like total internet strangers coming together and trying to solve a problem with money together. Maybe the GameStop movement wasn't the most successful instance of collective action in the markets, but it was the first very important, widely distributed one. What a lot of people don't talk about with the GameStop movement was that 6 months later, that same group of internet strangers actually managed to elect somebody as chairman of the board of GameStop in the annual shareholder meeting. And that's wild. There isn't a whole lot of precedent for that. And so we thought that was super cool. Right around the same time, a small activist hedge fund called Engine Number One got ExxonMobil, a huge oil and gas company, to give up 3 board seats in the name of renewable energy. And that might not seem intuitive, but they actually made a strong financial argument for why an oil and gas company with the United States transitioning to electric vehicles needs a transition plan to stay competitive, that Exxon's peer companies have a transition plan. And Exxon said, fine, it makes good business sense. And so we at the Troop team, we took a step back and said, whoa, these two things are so cool. Multiplayer finance and activism is just cool. It's very interesting, and it seems to be effective. So what if we built a community that helped internet strangers come together, pool their brokerage accounts, and actually do this on a repeated basis? And so out of that, Troop was born. Fast forward to today, we have two products. So Troop, on the right side, we were first a shareholder activism community app, and it's very much what I've been describing. It's a community platform. You can go to troop.com or download our native apps and meet a bunch of other strangers who own the same stocks as you and spin up brand new activism. You can do due diligence together, and we'll actually, if you get enough traction, get linked up with Troop, our research and legal teams, and help you file all of that with the SEC and make it real. 2 years into this project, one thing that we realized is that most people have significant wealth invested through bundled, passively managed financial products. Think ETFs, mutual funds, your retirement accounts. And those are relationships that should be high fidelity. We should be talking to our asset managers. We should be voting those shares. But there isn't really a good communication mechanism. And furthermore, those asset managers really don't know what it is we care about. So today, they vote with a set of voting directives that they build in-house, but they tend to not be representative of what we want. And so Troop aims to use Gen AI and machine learning to kind of bridge that gap, to both help asset managers at scale understand what it is we want, and in turn automatically vote all of our passively managed wealth in accordance with our values. And to understand the scale of this problem and perhaps why Gen AI is a good fit. So a lot of people don't understand this, but the top 10 money managers alone manage $37 trillion. That is spread across hundreds of millions of Americans, right, who never speak to these asset managers. And these asset managers are voting these $37 trillion on behalf of hundreds of millions of Americans at well over 3,000 publicly traded companies. Each of these companies has at least one annual shareholder meeting where they talk about a whole bunch of things that need to be voted on. They make important decisions. And there isn't really a good way to wrangle this much information. Many of you that have been hacking in this space or using Gen AI tools or watching the latest talks are probably familiar with some cool work that folks are doing, making chatbots talking to earnings reports. There was a famous one that blew up on Twitter where somebody made a chatbot talking to the Tesla earnings report and kind of asking about key risks and where the company did well, where the company could improve. And so we wanted to build on that research, but at a much larger scale, where the interface isn't chat, where we just figure out what it is that you care about, what are the directives of an asset manager, and how can we blend those two things together to basically automatically vote based on how you care at scale across all of these meetings for all of these people. And to do this, of course, one of the more elegant solutions is well-trained models and AI. And so in short, like so many of you out there, we're using RAG to bulk process SEC filings into structured features and summaries and labels that we can then downstream use in fine-tuned models and special purpose models that do voting, personalization, recommendation engines, and all of the above, just to make this a sane problem to manage and actually handle with traditional data science and data engineering tools. And so today's talk is very much about, I know you all see a lot of talks about RAG. This is the precursor step there. How do you actually make sense of terabytes and terabytes of information? How do you embed it? How do you organize it? And how do you set yourself up for success with RAG at scale? So let's start about the humble origins of the V1 of Troop's solution. So I'm sure this looks familiar to a lot of you. What we were doing was essentially using LangChain, huge fan of that tool, and specifically using the vector database Face, comes out of the Facebook team. It has implemented a lot of badass research around vector search, specifically searching like billion vectors without actually taking the distance of every one. And so we're a big fan of both of these projects. We wired it together and used their pre-built question and answer solution basically to automate extractions from SEC filings, which are in PDFs. And in short, it worked. It was super fast. We were able to pull structured data out with a little bit more finagling. We were able to get JSON and structured data out that's machine parsable. But we ran into kind of two key issues. One is that we were constrained by operating with only one filing at a time. So the way that Face works is you're responsible for chunking the information up, embedding it, and loading it into this local vector store. You're of course limited by how much you can fit in memory on that machine. And two, although Face does let you create embeddings and then persist them for use later, the whole loading and unloading of your vector database from long-term storage, that's on you to manage and write all of that code. And we thought to ourselves, there must be a vendor out there that is actually solving this at scale, where we've decoupled kind of the vectors that we have in memory from the larger corpus of vectors that we have at rest. And so that brought us to searching for a solution that met a few specific criteria. So one, like many high-end large volume data tools, we were looking for something that separates compute from storage. We wanted to have way larger corpus and way more embeddings at rest than we ever needed to query at once. Even when we're querying several companies or several filings at the same time, we never need to have the entire SEC's history loaded in memory. So we were looking for a solution that separated these two items. Two, we wanted the ability to scale the work out. And so, as I'm sure a lot of you face this problem, if you're working with traditional relational single node databases or document databases, you kind of hit a tipping point with your data where queries start to run really slow. And the only way to make it go faster is to buy a bigger node. And so we were searching for solutions that actually let you scale out, double your compute power by just adding more nodes. And so that was a pattern we were looking for. And then three, so our application runs in Kubernetes, we're in Google Cloud. Ideally, this would be something that we could self-host and run in our own Kubernetes cluster. Troop, our community app, is very much like a daytime app, right? And we have a ton of latent compute power. So it makes sense that we could run a lot of our data pipelines, for example, at nights and weekends, and take advantage of kind of the compute power that's otherwise not being used. And so we wanted to self-host it. And the other thing is, one priority of mine is that when I'm warehousing and building large data sets at scale, I prefer to own the storage. So we were looking for something ideally that let us write to a data store that we own. Ideally, it would be a bucket and cheap storage. And ideally, it would be written in a file format that's kind of open source and common. And so enter Milvus, right? Milvus elegantly separates compute from storage. We're actually able to write through the mini IO adapter straight into a bucket, which I love. At its core, Milvus is a distributed system. It runs on etcd, and you're able to add more nodes, and they communicate and share work with each other. And then finally, it was dead simple to install Milvus into a Kubernetes cluster. They've actually got a Helm chart. We got it up very quickly. And with a few configurations, we were running live. And so I was pleased to find a solution like Milvus because it fits very well into what I consider to be a mature, scaled distributed database. So let's talk about, I mentioned that we've got way more data at rest than we actually need to query at once, but let's talk a bit about what does it mean to actually ingest this much information. If we have any data engineers in the room, this is going to look a lot like your work. And I just want to help everybody fit the new kind of text to embedding to vector store paradigm into this distributed data paradigm. So how does it work? If you're familiar with LangChain, you're probably familiar with two concepts they introduce: a document store and a vector database. And a lot of folks are wrapping this into one solution. Some are actually co-locating the text payloads with the vectors, which is interesting. And some folks are actually just shoving all of this into a solution like Postgres. And look, if that works for your corpus, that's simple and it's awesome. If you're like us and it doesn't work though, you really need to split apart these components into their respective pieces and use the best tool for the job. And so, as I mentioned, we opted to chunk our text and then write that chunked text corpus into a bucket and partition it by time. So one detail of SEC filings is that they're released every day on the SEC database and website. You're able to see kind of for the latest, for example, Tesla filing, what is its ID and what day was it filed. And so we actually partition our raw text chunks by time. We then send them to an embedding model, take back those vectors, and we've created a collection in Milvus that is also partitioned by time. And so what we do is we actually write to a partition that matches the time partition of the raw text chunk. And if you're familiar with Milvus, what you do is you just write a bit of metadata into that Milvus vector document, and we're able to then query for vectors, pull that metadata, and then find the corresponding raw text chunk for use in a model. And just more generally, the key to using Milvus, in my opinion, at scale, I mean, you can get off the ground in 5 minutes with Milvus and it'll actually manage partitioning for you. But if you're going to write something of real scale and size, I think a key is spend a lot of time thinking about your partition scheme, whatever that is. It could be time, it could be by customer ID, it could be by user ID, but think about how your data is going to grow. And a key for are you partitioning correctly is if I want to randomly access the vectors or text payloads of a given document, can I directly target the partition where that data is written? So in our case, we know the date of the filing. I'm able to go and find those vectors. If you don't set any of this, Milvus's default partitioning is sort of a round robin scheme, and it will beautifully divide up your work into small chunks. The only downside of this is, as I mentioned, at scale, you probably won't be able to find just the partition where the data you're looking for is. So here's a quick diagram that illustrates how RAG works at Troop on top of Milvus, and some custom code that we've written to enable this to be a little bit more performant. So we start with a query. Perhaps we're looking for the list of board members that are being voted on at an upcoming shareholder meeting. What we do is we embed the query, and then we submit that to a custom Milvus server that we've written that sits between our Milvus clients and the Milvus server. What this does is it basically keeps track of the partitions that we're trying to read from disk when we bring them into memory. And if no other Milvus client has requested that partition in a while, it eventually passivates it from memory. So if any of you are running Milvus at scale in production at your companies, you may have faced this problem where two different Milvus clients loading the same partition into memory and working with it. If one of those clients then passivates it from memory while the other one is still working, you can kind of run into contention. And all of this, I'll mention, is to avoid just loading the entire collection into memory, which for our problem, we can't afford to do. And so we've written this custom Milvus server that basically manages the loading into memory and its passivation when nobody's using it. We then, like traditional RAG, pull the metadata off of those vectors, fetch the raw text payloads from the bucket, submit it to the LLM as context, and then we retrieve a result. This custom Milvus server, so it's written in Go. It's actually something that we've been talking about contributing to the Milvus project. Right now, it's very custom tailored to kind of Troop's use case, but if that's something you're interested in hearing about, hit me up after the call. I'm happy to walk you through how that works. And as I mentioned, we are talking about internally contributing this to Milvus. Next, so as I mentioned before, a key goal of Troop's machine learning program is creating a reasonable data lake of clean information. And our raw data, these PDFs can span hundreds of pages. Some of them can be, hundreds of megabytes large. And a goal here is to basically summarize and compress the information down into something much smaller, predictable, and manageable, especially for use in fine-tuning and custom training smaller models downstream. To that end, one thing we need to do is essentially create summarization prompts and pipelines that take large amounts of information and summarize them to much smaller payloads. And if any of you are working with this sort of workflow on top of like a RAG architecture, you've probably faced a common question either internally or from your stakeholders. How do you know if the summary is right? As a larger pattern, the question they're asking is, how are you evaluating the efficacy and accuracy of this black box extraction that you're running? And we found a sort of interesting way to do this that I want to share. And I think this kind of is the beginning of showing the power of embeddings and kind of how we think about embedding for a lot more than just search. So in the case of a summarization or data compression prompt, one thing that you can do is take the result of your model, perhaps it's a paragraph summary of 20 pages of data, embed the summary, maybe run 3 variants of your summarization prompt, embed them all, and then take the prompt or the model where the average embedding of your result is most similar to the embedding of your source material. In plain English, what that means is that the topics and concepts and entities talked about in your summary are the most similar to that of the source material. In a way, you've lost the least information. And so we think about summarization as a compression algorithm, and evaluating it should just be topically, do they talk about the same things? So at scale, we're able to run multiple variants of summarization models and then basically compare with a machine, evaluate with a machine which one's the most effective by using embeddings. We then actually take those embeddings of the results and write them back into Milvus for another use case that we'll talk about in a moment. Similarly, I'm sure many of you are faced with this. So human labeling is expensive. Human evaluation of labels is very expensive. One thing that's interesting, though, is the larger Gen AI and ML community regards GPT-4 as pretty accurate for most general use cases. It's also the slowest model. It's expensive. And so how can we leverage a more expensive model, a fancier model like a GPT-4, to actually evaluate and train cheaper models? That's kind of core to Troop and our architecture, how we work, and I'm sure that's the same for many of you. So similarly, we're able to use an expensive foundation model on a subset of the data to produce summaries, labels, categories, embed those outputs, and then actually compare the result to the embedded output of much cheaper fine-tuned or custom-trained models. And finally, so, as a data engineer and once data analyst in my career, it's been a hot topic for a decade now, introducing data democracy, using embeddings, and how do you basically give your entire team access? You've built this wealth of information, this huge data lake, all these embeddings, all this information, these results are also embedded. How do you give your team access to it? For our transactional data, the things coming in from Google Analytics, our application metrics, all of that is being fed into a traditional data lake in BigQuery and exposed with Looker. But for something unstructured, like text payloads, you need to basically give your team access directly to the RAG model, in a sense. And so in addition to Looker for internal data discovery, Troop has also introduced a simple Streamlit application. And what we've done with this app is just pointed it directly at Milvus and our document store so that the team is able to run ad hoc queries against the text payload and actually do, their own custom RAG pipelines, taking information from our embedding store and creating their own prompts with one of the main foundation models today. And so, this Streamlit application, once we had everything else stood up with Milvus and the data lake and everything else, this entire application probably took an afternoon to put together. More than happy to talk to folks after the call about how we did this, but I suspect that most of you, if you have any, sort of front-end team, would be able to hack this together pretty quickly. Actually, most of the code, you just need to know Python to set up Streamlit. The front end comes for free. So highly encourage doing this. And it's sort of taken Milvus from a tool that's just for data pipelines to something that's actually exposed to our internal team. And I suspect it's something that will eventually make user-facing, although from a product standpoint, we haven't totally figured that out. All right. And with that, want to say thank you, Steph, for inviting us to talk about Troop and how we're using Milvus, and specifically how we're using embeddings to basically compress and make sense of our corpus of text, making machine labels and verified labels, and powering kind of our downstream fine-tuning and machine learning program. So thanks, Steph, and thanks everyone for watching.
Thanks, Jen. Really appreciate the presentation. Now we're open for Q&A. Feel free just like paste your questions at the bottom of the Zoom bar. Let's give a couple minutes and to see what the questions are coming. Okay, the first question. Given the array of value in the US, are you worried about the bias in the embeddings and the LLMs you use?
So the question is, given how many different types of people there are we worried about the LLMs and embeddings having bias? It's something our team talks about a lot, actually. And so much of the work that we put into this is actually to, we use techniques like grounding and, as I mentioned, like bringing human verification into the fold so that we can actually fine-tune and train these models to be able to answer for specific viewpoints. So as an example, one thing that we did early on in this project is make sure that our LLM and embeddings engines are actually able to represent the entire US political spectrum of values. And we consider success and accuracy in each of those personas as independent of one another. And so we prioritize it. So in short, yes, we very much care about that. We are worried about bias, but we've been able to fine tune the models to speak to a whole array of values.
Cool. Let me see if there's any other question here. Would you ever make a version of your own chat Streamlit app public or user facing?
Yeah, so as I mentioned with the Streamlit app that we've built, I do think that chat can be a clunky interface for a lot of data tools. Like sometimes you put a chat interface in front of a user and they don't even know what to ask. So we're starting with it as an internal tool because our internal team is very focused and they know what to ask. I can 100% imagine a future version of Troop where there's a chat interface for asset managers to collect information about their clients, and maybe even for everyday investors like us to interface with the asset manager at scale. It's something we're talking about, and I think if the general public wants us to open up our Streamlit app, we'll seriously consider it, and happy to do so.
Like let's say if anyone who participate right now are thinking about to build such things, is there any specific tips you want to share?
Sorry, Steph, could you repeat that?
Oh, actually, I see another question here. How do you deal with lots of data across document matching from vector source with the limitation of token length in LLM? Summarization is limited, I guess, in LLM. That's what this person is saying. Thanks,
Yeah.
Vincent, for the question.
Yeah, totally. So it's a hard problem. I think the way that Troop has built a solution that maybe deviates from the Hello World examples is we break down the problem into multiple steps. So step one is, let's say you have an 100-page PDF, right? And generally the sorts of things you're trying to extract from some unknown pages within the PDF, one example of a solution is to actually just roll through every single page, right, and pull out a mini extraction of the topics in that page. And so you can kind of think of it as a map reduce problem. Take every page, map it to a smaller amount of data, or every chunk to a smaller amount of data, run extractions on that, and then, iteratively do this until you've boiled it down to a much smaller summary. And at each step, a key point is your evaluation technique. So how are you evaluating the efficacy of your summary? Because you're right, Vincent, summarization is limited and hard. One really cool way to do it that uses embeddings in Milvus is to just embed the results of your compressed data and then compare it to the source material, the embeddings of the source material. So if the embeddings are very similar, it means that you've probably captured most of the concepts in your extraction that were in the source material. And if you actually look at the larger, like Llama Index just gave a talk about this, using embeddings to evaluate models is becoming an increasingly popular technique.
I hope that answered Vincent's question. Then the next question I have here is, how do you think personalization via AI will change finance and asset management in the coming years?
I think that the whole way that we interact with finance is about to turn upside down. It very much went from an experience, like a consumer experience, where the average person doesn't know a whole lot about what's going on in the finance world, and especially for our business in what's going on in shareholder meetings. Like almost nobody that we meet reads the voting packets and understands what's coming up at an upcoming shareholder meeting. And so it was very much on what's called an asset stewardship team to know what's going on and make the right choices on your behalf. I think with AI, the opportunity for personalization is amazing because you actually can have at scale sort of automated conversations and data exchanges between the folks that manage your money and the underlying investor. And so I think we're moving towards a world where both in the governance world where Troop is focused, but also the larger asset management and finance world, we're going to start seeing a lot more products that their competitive angle, the way they sell themselves, is personalization for you. And I think that all of that is going to be enabled with AI.
Thanks for sharing your vision. Do we have more questions here? Let me check. Well, if there's no more question, we'll conclude this session. Thank you so much, Zen, for joining us, and thanks for everyone participating in this webinar.
Thanks, Steffi, for having us, and thanks everyone for attending. My contact info is on the screen. Please hit me up if you want to chat. Thank you.
Thank you. Looking forward to more webinar with us. Thank you. Bye-bye.